Good morning, students. Today we are going to discuss higher order differential equations and general solution with its component complementary function, and in particular part 3, which will be the complex roots which are non-repeated, and we'll also see how to deal with multiple complex roots which are non-repeated. Previously, we covered two parts in this same complementary function, which was for real and non-repeated roots, real and repeated roots. So today our focus would be on the complex roots of auxiliary equations. So let us start with the general consideration of second order differential equation. So again, for simplicity, I am considering second order differential equation y double dash plus c1y dash plus c2y equals to r of x. All considerations are standard, like y is dependent variable on independent variable x, c1, c2 are arbitrary constants, and rx is a random function of variable x. Now, the first step is to consider the operator form of higher order differential equation, which can be achieved by defining d raised to n as d raised to n upon dx raised to n. So, on the left hand side of equation, as we have y double dash, it will be d square of y. Second part is y dash, which is d of y, and last part is c2y, and that is equal to r of x. Now, if I consider the left hand side, then I can take this y outside the bracket, which will give me d square plus c1d plus c2 times y equals to rx. This will be the common practice for all higher order differential equations, and that will give me the general form of higher order differential equation as in differential operator f of dy equals to r of x. Now, let us consider the auxiliary equation. Once we derive the operator form f of dy equals to r of x, to find complementary function, we need to focus on auxiliary equation of this differential form, which can be derived by considering this f of d and equating it to 0. So whatsoever be the combination of d and constants in this part, equate it to 0. That equation is known as auxiliary equation or characteristic equation. And now the next step is to find the roots of. So while finding roots of this equation, we may receive four possibilities. It may happen that roots of these equations are real and distinct. Roots of these equations are real and repeated. These two are our previous cases. For this real and distinct root and real and repeated root, I already posted separate videos. You should go through all those videos first. Today I am focusing on this part, which is part 3, complex and distinct roots. And in the next video, we'll also see how to deal with complex roots which are. Let us focus on this third case of complex roots. So, suppose we have this auxiliary equation f of d equals to 0, and equating it to 0 will give me complex roots. Now we know that complex roots are always in a pair of form alpha plus or minus I beta. In this case, there is a particular role of this part beta also. Now, suppose we have only two complex roots. In that case, the complementary function will take shape of this type. E raised to alpha x. Alpha is the real part of our complex roots into C1 times cos beta x. Beta is the imaginary part of our complex roots plus C2 times sine beta x. Again, that here our equation is of second order and we have two arbitrary constants. So the rule of total number of constants in any complementary function remains same irrespective of its nature of real or complex, which simply means that the total number of roots of auxiliary equation or the order of differential equation will decide the total number of arbitrary constants. Now, you can always remember it like this, that if there exists a complex roots, then associated with exponential function. In case of real roots also, we have seen that the real roots are always associated with exponential function. If there exists imaginary part, then there will be cos and sine into the complementary function. Let us consider example. Let me take first example y double dash plus y equals to 0. Now in this case, the given differential equation in operator form is d square plus 1 times y equals to 0. Considering complementary function and for that, auxiliary equation would be f of d equal to 0. If I take f of d equal to 0, it will give me two roots which are complex by nature. These roots are 0 plus or minus I. Here we can see clearly that alpha is nothing but 0, which is the real part of the roots, and beta is nothing but 1, which is imaginary part of the root. And so we can fit e raised to 0x, which is the real part of the roots, times c1 cos 1 into x plus c2 sine. This simply means that real part is always associated with exponential function and imaginary part, they are always associated with sine and cos. This is how you can find complementary function for complex non-repeated roots. Let us consider one more example. Suppose we have d raised to 4 minus y equals to 0, which simply gives us d raised to 4 minus 1 times y equals to 0 as differential operator form, and then to find auxiliary equation f of t equal to 0. Now, if I take f of t equal to 0, it simply gives me by perfect square technique on the left hand side d square plus 1 d square minus 1 equal to 0. So that means now we have four different roots. The first root is 1, second root is minus 1, third and fourth root are imaginary roots, or you can say complex roots, 0 plus or minus I. So these first two roots are by this factor d square minus 1, d square plus 1. Again, let me recall that there is no rule for the order of roots of this auxiliary equation. You can consider complex roots first and you can consider real roots later also. That is also valid consideration. Now, let us focus on roots of this equation and then let us discuss how to write complementary function. So, at a time we have one non-repeated real root, so I am write down complementary function for this first part, which is c1 e raised to x. Second root is minus 1, so I am taking c2 e raised to minus x. The third and fourth root are complex roots, 0 plus or minus I. So I need to take case number 3. So here you can see the alpha or the real part is 0 beta or imaginary part is 1. So it is e raised to 0x, which will turn to be 1. The cos of x into c4. Again, you can see clearly that order of equation is 4 and there are 4 arbitrary constants c1, c2, c3, c4. These first two roots are following first case, non-repeated or distinct real roots. So for that we have that first part of complementary function, whereas this third and fourth roots are complex, and so for that we have case number 3 of complementary. Let us consider one more example. Suppose we have y raised to 4 plus 4 equals to, sorry, here it must be y raised to 4 plus 4y equal to 0. In that case, what will happen? We'll get d raised to 4 plus 4y equal to 0. And then auxiliary equation would be f of d equal to 0 with d square plus 4 equals to 0, which eventually will give you minus 2d whole square. So that means I'm adding and subtracting this 2d whole square to make it perfect square. So finally, it will give you d square plus 2d plus 2, d square minus 2d plus 2 equals to 0. So it gives you this of the roots. The first root is minus 1 plus or minus I. Second roots are 1 plus or minus I. So that means I need to write down this complementary function separately for this first two roots and for last two roots. So let me consider the first part. So here alpha is minus 1. Accordingly, it is e raised to minus x. C1 times cos of 1x, 1 is beta, plus C2 sine of 1x, plus alpha is 1 over here, so it is e raised to 1x into C3, beta is 1, so cos x plus C4 sine x. This is how you can deal with complex roots. I hope this part was easy for you. Now, let me give you one situation. Suppose you have two repeated real roots and a pair of complex roots. In that case, how to write down the complementary function? That will be for your exercise. If you have any difficulty, you should again go through the video. You should pause and ponder in between, and you can check how to deal with real distinct roots along with complex pair, how to deal with repeated real roots along with complex pair, and how to deal with two distinct complex roots. Thank you.